Okay, off we go. So, starting with a new section now, 6.3. Reminder, last time, what did we talk about? We talked about Green's theorem, and there's some cool facts about Green, various applications and interpretations, blah, blah, blah. The big idea, right? The underlying, the thing that makes it work, ultimately. The idea of an accumulating quantity. Right? Once you know you have an accumulating quantity, then you can think of it as a kind of a stuff, even if that's nonsense. You can think of it as a kind of a stuff. You can imagine the corresponding notion of density, and you can compute it with an integral. And that's just how the Green's theorem is the result of applying that to. Why don't I click back to it real quick? Green's theorem is what results when you apply that idea to the idea of boundary circulation, right? So the quantity in question, when you're talking about Green's theorem, boundary circulation, that is a quantity that you define on areas. You give me an area, whatever the area might happen to be, I can say, okay, for that area, here's what the boundary is. The boundary is a curve. We're going to compute a circulation around that curve. That's our quantity. All right. So again, you apply this idea, you apply those ideas we discussed to the accumulating quantity, boundary circulation, and the result is Green's theorem. Okay, so now let's back to where we are picking up from last time. Here we go. Here's a new theorem. It's called the fundamental theorem of line integrals. You're going to notice at a very quick glance, it looks an awful lot like the fundamental theorem of calculus, doesn't it? Just as a casual glance, right? And by the way, the name, therefore, really makes sense. Fundamental theorem, it looks just like the fundamental theorem of calculus. But of course, this one obviously involves line integrals. So, the big idea is that if your vector field is a gradient. And by the way, they like the term conservative. We've talked about that before, I think. To me, the more natural word is gradient, because it's a gradient, right? I don't know why we need another word there. Anyway, but if you have a gradient field, then a line integral is computed by, how much does some other function f change? Specifically, that function being the function whose gradient you were looking at. Right? So it's almost like, it's kind of like the fundamental theorem of calculus. It's almost like it's saying the integral of a derivative is the original function, right? Lots and lots of the same earmarks. Okay, so reminder, we have a new point of view that I was pushing last time on how to think about the fundamental theorem of calculus. Think, if you would, again, there's different time, different appropriate points of view for different time, different place. In this context, don't think of the fundamental theorem of calculus as a tool for computing integrals. Think of the fundamental theorem of calculus as a formula for how to represent this accumulating quantity called change, and how to represent that as an integral of change density. Right? Again, I know that's a weird take. Very weird take, but it sure is handy when we're trying to understand vector calculus. Okay, so same thing here. This, notice, is change. Right? And what we're going to develop here is we're going to say, change. We're going to realize it's an accumulating quantity, and we're going to reinterpret this integral as saying, we're adding up. We're integrating change density in a sense. So here we go. First of all, how do I know? First of all, let me establish this notation. I like using a capital Greek letter delta to represent change. We use capital Greek letter delta for that purpose in other contexts, so I'm just kind of stealing it for this purpose. So there you go. And I claim change is an accumulating quantity. The whole is the sum of the parts. This is an easy observation. If you want to know how much the function changes overall across some curve, right? Well, that's going to be how much the function changes on the first half of the curve plus how much the, plus how much the function changes on the second half of the curve. Right? And it's pretty intuitive if you think about it. Right? I mean, again, I like to, whenever I am looking at a curve in 2 dimensions and we're keeping track of some function, I like to think of the function as being altitude. I like to imagine that the curve is a mountain road, and I'm driving along the mountain road. And yeah, the amount of altitude that you gain in your first hour of driving, plus the amount of altitude you gain in the second hour of your drive, well, of course, that's the total amount of altitude that you've gained. Okay. All right, so I think that's pretty easy buy. And now, nice little observation. We already know how to compute that change density because of this old formula right here. This is an old formula. It's written a little differently, but it's an old formula from chapter 2. This says if you've got some function f and you want to know how much that function changes, well, we make linear estimates. Keep in mind a differential is a linear estimate. We make linear estimates of how much the output changes by dot products with the gradient. Right? So this, again, chapter 2, old news. And then all I'm going to do, pull a little fast one here. I'm going to rewrite dr as TDS. Right? It's we've pulled that little fast one multiple times in the past. And doing so, now, very conveniently, output change and size are related by this factor. Right? So if you want to know literally change per unit size as you drive along the road, and of course as you drive along the road, as you move along a path, size is length. Change per unit size, there it is. It's that formula. It's gradient dot unit tangent vector. And okay, well then, boom. I mean, this observation here, I can plug right on in to the observation, and we have this, existing observation that change is an accumulating quantity, and you just plug that in, right? Oh, I admit, look at what I did. I'm sorry, I missed the, Don't forget the DS, right? So we've got change is change density times size. So just plugging that in, and then, let's pull our little fast one again, and let's remind ourselves that TDS is DR, and out comes our theorem. Change is an integral of a gradient, as stated. How are we doing? Is everybody on board? All right, so that's why the theorem's true, and I've got an example ready to go. Before I show you the example, I want to plant a thought. The following thought is going to be important later. But I like to plant thoughts early sometimes so you can kind of be mulling on it and chewing on it, and so I don't broadside you with a weird thought later on with no warning. So here's the weird thought. We've already observed this, right? And so again, this is density because it's what you multiply by size to get, excuse me, what you multiply by size to get stuff. That's what a density is, stuff per unit size. Now, let's take a look instead, though, at this. And how can I interpret what this thing is? Not gradient.t, just the gradient by itself. What is the gradient by itself? What is this dark blue formula? What's the reasonable interpretation? What's our take on this from the point of view of density? And here's my take. I think this is very reasonable ultimately. This dr, I'm going to call oriented size. Now, let's take a moment to dwell on what are you talking about, oriented size? size is a scalar. It's intrinsically a scalar. So, okay, yeah, right, granted. Well, this dr, being as it is, TDS, is a size times an orientation. It has both, this dr thing has a size and an orientation. That's what dr is. And if it is a size and an orientation kind of wrapped up together, I think oriented size is a reasonable thing to call it. Right? So with that, again, that's a take. You can decide for yourselves how hot that take may be. Well, then the gradient is the relationship between stuff and oriented size. And so I propose that it's reasonable to call it an oriented density. It's the density in a sense, but with the understanding that you've got to have an oriented size to make sense out of it. It's just a thought. I'm just planning a thought. Again, this will be important. This is going to be a sort of a stepping stone when we get to a significantly more geometrically challenging example, namely when we get to Stokes' curl theorem. Having a reasonable sort of stomach for this idea will really help when we start trying to make sense out of three-dimensional curl and Stokes' curl theorem. So that's my incentive there. Okay, all right, but anyway, let's plug and chug. All right, so here's our first plug and chug example. We're going to look at this question. It says compute this line integral. Let me remind you, as we've noted previously, that when these kinds of questions come up, they usually don't announce themselves as a, here's the question and part of the answer. Right? So very often questions will say, compute the following line integral using the fundamental theorem of line integrals, or compute the following line integral using Green's theorem, or something like that. This one doesn't. And by the way, life tends not to. Right? So in your practical experience, when you're working engineers or whatever field you end up going into, when you need to compute something, it usually just shows up as this is the thing I need to compute. You don't have any obvious help on what path or what tools to use. So you could take the parameterization and plug it in, and take the parameterization and compute your R prime, and do the usual pullback thing, plug and chug, and that's going to end up with some trig integrals that are doable, but a little tedious perhaps. So the better path, the better idea here is going to be to realize that this vector field, our integrand here, is a gradient. And specifically, it's a gradient of this function right there. Now, this is easily checked. Right? Y'all can take this function. Y'all know how to compute gradients. Just take the gradient of this x squared, y squared. And sure enough, oh my gosh, you get exactly this. So our question is not just to compute a line integral. Our question here is to compute a line integral of a gradient. And that's what we have this awesome tool for. Right? If you want to take a line integral of a gradient, then all you got to do is find, y'all will recall what I like to call the anti-gradient, the thing whose gradient is your vector field. Just find that anti-gradient, right, and plug in the endpoints and subtract, just as if you were doing the fundamental theorem in calculus. So that's what we're going to do. We've got our anti-gradient. Our anti-gradient is that right there. That is our wrong color. That is our F. And we just plug in the endpoints and subtract. There's nothing to it. Boom. Everybody see how fast that was? That was really fast. Much better than having to deal with trig integrals, I think. Now, to be clear, how to know where these endpoints are? Well, keep in mind that this path starts when t equals 0. You plug in t equals 0, and that tells you your starting point right there, which, of course, goes there. And then, of course, our curve ends when t is pi. And you plug that in. That gives you your endpoint here, which, of course, you plug in there. Okay. Now, I swept something under the rug here. Did it on purpose. Right? My goal here was to demonstrate how streamlined and awesome this theorem is, which it is. But I did sweep under the rug. Where did I get this x squared y squared thing from? Right? Where did that come from? I pulled that out of a hat. Right? And you might very reasonably be thinking to yourself, well, in practice, if I'm going to use this theorem, this x squared y squared wasn't given in the statement of the question. I'm going to have to dream up for myself what is that anti-gradient. How do we find anti-gradients? And we will address that. And it's going to be near the end of today's lecture. Well, it's going to be near the end of this section. Anyway. Okay, so that discussion's coming. Okay. Here's a related idea. It does not appear to be related at first glance, so for the moment, let's just view this as being a new idea. It's called path independence. I'm going to start with a super obvious statement. I think this is pretty obvious. If you want to compute a line integral over a curve, well, it depends on the curve. Well, doesn't it? Well, of course it does. That's where I'm computing the integral. Obvious. I mean, come on. Of course it depends on the curve. Right? Well, analogously, if you want to compute an integral in single variable calculus, well, it depends what your interval is. Well, of course it does. So here's the amazing thing. Really shocking fact. There are some special vector fields. Let's see, I'm going to use orange for this. There are some vector fields. And what I'm about to describe is a property of the vector field. Amazingly, only the endpoints matter. That's shocking. You're telling me that I can, as long as I take a given starting point and a given ending point, you're telling me that I can compute on that curve, or I could compute on that curve, and you're telling me I'm going to get the same answer. There are certain vector fields where I get the same answer on either curve. They're totally different curves. Surely the curve should matter, shouldn't it? Right? We just got through agreeing. The line integral should depend heavily on the curve. So this is a shocking feature, right? And vector fields that have this property, and keep in mind this is a property of the vector field. Vector fields that have this property are called path independent. Our book likes to say has path independent line integrals. To me, that's unnecessarily bulky terminology. So I'll just say path independent. The more common term is to say it's a path independent vector field. Okay, so it's an amazing property. How could this ever possibly work? And by the way, here's how we write it down. These, again, fancy vector fields have the feature that pick any curve you like, as long as the curve have the correct starting point and ending points, as long as they have the same starting points and ending points, pick any curve you like. All right, so I like to start this subsequent discussion with an example of when it doesn't work. I have found over the years that when we talk about path-independent vector fields, there is a certain phenomenon that happens where a lot of students just misunderstand the point. I am not saying that all vector fields have this property. Oh, of course not. Definitely not. In fact, the great majority of vector fields do not have this property. So just to be as bluntly obvious as we possibly can, here is an example of a vector field that does not have this property. And look how easy it is to find a vector field that does not have this property. What an easy little vector field. And persuade yourself that it looks like this. And then I'm going to set a couple of points. Here's a shared starting point and a shared ending point, and we're going to look at two different paths. We're going to look at that path and this path. And if this were path independent, we would need these to get the same value, and they're not going to. And again, this should not be surprising. This is kind of what you ought to expect to happen. Now, it's an easy calculation. Let's look at this first integral on C1. Well, on that edge, the vector field is 0. On that edge, the vector field is perpendicular to the curve. That line integral has to be 0. Okay, well, fine, whatever. Now let's look at this other curve here. On that edge, the vector field is perpendicular to the curve, so nothing there. But if you look along this edge, there's pretty clearly some positive line integral along in there. The fluid is clearly flowing along the curve. The line integral on that edge is unambiguously positive. And what the value is, you can work it out. It's not really the point. But the point is it's clearly positive, right? And so these two line integrals, on this curve, it's clearly positive. On this curve, it's clearly 0. And these are not the same. So this vector field is not path independent. And the big purpose of this example, of course it's not. Most vector fields are not. All right, so that warning aside, it turns out that there's a very huge category of vector fields that are path independent, which of course you probably guessed. Why would we talk about this property if it wasn't important? So in fact, gradients. You got to be continuous. Okay, yeah, sure. Regularity conditions come up from time to time. It's not really what we're focused on here. But gradients, it turns out, are path independent. So let me show you why. It's ultimately a pretty straightforward argument. Now keep in mind, if you want something to be path independent, then if you pick a start, and if you pick an end, and if you look at two curves that have the same start and the same end, I need for that first integral and for that second integral to be equal. Now, wow, really? I need these two integrals to be equal? They're on totally different curves. How can these integrals be equal? Well, we're doing an integral of a gradient. When you're doing an integral of a gradient, we can apply the fundamental theorem of line integrals. Right? The fundamental theorem of line integrals applied to the green integral gives an expression that only depends on the endpoints. The fundamental theorem of line integrals as applied to the blue integral gives the same exact expression that only depends on the endpoints. So those are the same. Is that cool? It's a lovely little argument, right? Very cool argument. I'm going to call it a little bit unexpected. Now, you remember when we first introduced this idea of path independence, I said it's related to the fundamental theorem, but I wasn't clear why. This is why. Right? The fundamental theorem is the tool that allows you to show that gradients are always path independent. Continuous gradients are always path independent. Okay, and by the way, it goes both ways. Not only is every continuous gradient path independent, but every continuous path independent field is also a gradient. There's other little regularity conditions about not having singularities, and again, that's not really what this class is about. Okay. Excuse me. Okay, so neat fact. Now, here's a different point of view on path independence. This one ends up being useful also. It's a little bit less natural. It's a little bit less naturally connected to the term path independent. But here's the thing. If you have a path independent vector field, and keep in mind that means that the green integral and the blue integral are going to be equal, right? This is what path independent means. Well, if you think about it, two things being equal is the same as saying that their difference is 0, well, of course. And, well, wait a second. This says we're going to go around C1, and then that we are going to continue by going along C2, but backwards. So let me do that again. We're going to start along C1, then we're going to go backwards along C2. And apparently that integral on this sort of combined curve, well, it represents that difference, which we just agreed has to be 0. So here's the alternative take, a different way to define what we mean by path independent. Path independent could be taken as all circulations are 0. Right? And the curve that we have here that resulted from our little fast one that we pulled, it starts and ends at the same point. That means it's a closed curve. And line integrals on closed curves are circulations. Is that cool? Okay, now, who cares? What's the relevance? Here's, I think, a nice example of how that particular take is handy. I don't know if y'all are familiar with the work, the art of this artist named M.C. Escher. He did a lot of fun stuff, depending on, what you enjoy. Right? I like the fact that there's kind of a mathematical element to some of what Escher did. Now, this is one of his very well-known pieces of art, and it depicts a kind of an illusion, a little optical illusion, right? And it's perfectly self-evident. Well, correction. When you look carefully at this, you'll very clearly get the, hey, wait a minute here, right? And let's just dwell on the, hey, wait a minute, that ain't right aspect of things. That's uphill. That's uphill. That's uphill. Wait a second. These NPCs walking that direction around the stairs, they keep going up, but they keep coming back to the stairs. What? Nonsense. Right? Okay, well, that's really, I'll say that our reaction to that illusion is really just reflecting how we all, on some level, have a natural intuition for this idea of path independence. In particular, that when you go around in a loop, you come back to the same place. And let me just flesh that out. Let's talk about what I like to call the steepness vector field. And by steepness, all I mean is the vector field that points uphill, whose magnitude is, how steep it is in that uphill direction. And of course, we know from long ago that's the gradient of the altitude function, right? So we've got a gradient, right? We know gradients are path independent. And if you think about it, the steepness field .dr is keeping track of your altitude changes. So altogether, if each one of these represents an altitude change, right? And of course, every step along in this path, we seem to be seeing positive altitude changes. I mean, the Escher's art makes it look like we're adding up a bunch of positive values. But the idea of path independence tells us that these allegedly positive values have to add up to 0. And of course, that is obvious nonsense. Right? So it's a nice little take if you want to think about path independence in the context of this Escher art, then this circulation point of view, right, is more convenient than saying that the green integral is equal to the blue integral. It's just more convenient to have this circulation point of view. Okay, how are we doing? Is everybody on board? By the way, if you aren't already familiar with M.C. Escher, look him up. It's lots of fun, really well done little illusions and really interesting stuff. So. Okay, so, right, who cares? Why do we care about path independence? And I will point out that it's a really conceptually important idea for various reasons. There is a physics point of view on this. I'm sure y'all are familiar with the idea of potential energy. Right? Potential energy relates to forces. Right? So the most well-known example, well, the most, among, commonly, the real world, is gravitational potential, right? Gravitational field, and talk about potential energy. And if I lift my stylus up to here, now it has more potential energy, and down here it has less potential energy. Well, in order to make sense out of that, the way I compute is I think, okay, well, how much work does it take for me to lift to over here? And if you think about it, if that's going to make any sense at all, then whether I lift by way of this path had better tell me the same amount of work as if I lift by that path. Potential energy only makes sense if you have a path-independent vector field, right? So this is a conceptual observation, right? That didn't help me to compute anything, but that concept, that conceptual idea of path independence allows me to make sense out of the idea of potential energy. And of course, as anyone who's taken a mechanics class knows, the idea of potential energy is really important for computing stuff, right? So this is one of the reasons path independence is super important, is because it's useful to develop valuable concepts. That said, computationally, like as a direct tool for computing stuff, if you think about it, if you have a path-independent vector field, well, we just got through discussing, that means it's a gradient. And if it's a gradient, you could use the fundamental theorem. And the fundamental theorem is a sledgehammer for computing stuff. So, who needs it? Who needs path independence as a computational tool? We already have an awesome such tool, right? So it's kind of like, I already own a hammer. Why do I need a different hammer? Right? What's the point? Well, the reality is that sometimes the fundamental theorem can be hard to use. Notice that the fundamental theorem does require that you find the anti-gradient, and there are some instances where finding the anti-gradient is actually not desirable. Sometimes that's hard. So sometimes the fundamental theorem is not a sledgehammer. That's the big idea. So let's see how such a computation would work with path independence. Now, fully granted, this right here, it's not that much trouble to find the anti-gradient. And I'll bet you could, go into smart alecky mode and play some clever guessing games, and you could totally find the anti-gradient. Yeah, of course, I know. My purpose here is to show how to use path independence to compute an integral. I fully recognize we don't need it in this case, but there are situations when you will. Okay, so here we go. We've got a given. By the way, it's given as path independent. We'll talk later about how I could possibly know that. And we want to compute an integral over a particular curve, namely that curve. How do I compute that integral? Well, again, you could brute force this. You could parameterize that blue curve. It's going to have trig in it. You're going to have trig all over your integral, and again, it's not that you can't do that, but all else being equal, we kind of prefer to avoid that. And in uglier cases, it would make the problem intractable. So I'm going to call that a bad plan. That said, we know that this is path independent. Path independent means that as long as I don't move the starting and ending points, this curve, this curve that I was asked to compute on, I could use any other curve. I could use that curve if I were, a masochist. right? I could use that curve, or I could use, suit yourself, go crazy. So how do you know what path to choose? Well, let your own self-interest guide you. I mean, pick any curve you like, right? That's the whole point of path independence, is you get to pick. So obviously, self-interest in mind, you're going to pick the easiest path you can think of, and I think it's kind of hard to beat a straight line. Super easy to parameterize in this case. Super easy. T goes from -1 to 1. Ultra easy to parameterize. Is that cool? Yeah. So we pick that curve, easy to parameterize, and then I'm going to say it's an easy plug and chug. I'll point out a couple of quickie things about this observation. There are some neat uses of the following observation. The following comes up. Notice in my new curve, you don't even need to look at the parameterization. You could just see right here, looking at our new curve, y is always 0. Again, there it is. It's on the x-axis. Y is clearly always 0. So plug that in. So good. Simplifies your vector field very nicely. Another quickie observation that I think is, good time to observe. As I move along that curve, y doesn't change. And namely, dy is 0. Because, again, keep in mind what dy is. dy is a way of representing how much y changes along that given little piece, whatever given little piece of curve you're looking at. And that's just not ever going to be anything but 0. Okay, so those two simplifications, give me a quick second. Those two simplifications allow me to turn the problem into an instantaneous 0. And if you were to actually pull back through the parameterization, you would still get the same answer with mostly the same convenience, but this is a little quicker. Yeah?
Are you dotting it with r prime of t?
With dr. But dr is r prime dt. Yeah.
Okay, and if you were to do it with r prime dt,
Yep.
you would just dot it with 1, 0?
Yep, that's right. Well, that's right. It'd be 1, 0, and then times dt. Yep.
Yeah.
Totally. Yep.
So that will give you 2xy integral dt.
Yes, and y will still be 0. Because you got to plug in. So yeah, so you get the same result.
Okay.
Yep, absolutely. Cool. All right, so every so often, yes, you can use path independence for a direct computational purpose. It's not really the point. The point is it's a really important, conceptually valuable idea. Okay. All right, now here's a cool argument. It's what I like to call a local test. Actually, I think the book calls it this, and I just like that the book calls it this, so let's put credit where credit's due. This addresses the question, how do you know when a vector field is path independent? Again, up here in this example, I just, gave pre-information that this is path independent. And again, if the algebra were different, it would not be at all clear whether that is or isn't. Okay, so it turns out there's a wonderful way to answer this question, and let me start by reminding y'all that we already know these three things are equivalent, right? We already know that gradients are path independent and vice versa, regularity assumed. And we know that path independence can be rephrased in terms of circulations always being 0. Yeah? So we already know that. Okay. And here's the beautiful little slick move. Closed line integrals, aka circulations. Green's theorem tells us we can compute those with a double integral of curl. So if the closed line integrals have to be 0, well, that means that these double integrals have to be 0. Yeah? Everybody see how I did that? And now let's look at this statement. And I want to think in particular about this expression, the curl. What does this orange statement tell me about this curl function? We've got an integral that's equal to 0, but here's the thing. This domain could be any domain, right? Where all this came from was, any path, right? That ain't regular, but any path. So that, closed curve, of course. And so not only is this saying a certain integral is equal to 0, what it's saying is that all double integrals of this function, always 0. No matter what domain you give me, double integral is 0. Now let's just take a quick pause and let's think, how many functions do you know that do that? Right? Continuous functions where all of the integrals are equal to 0. And the answer is there is only one such function, and that is the 0 function. All right, so this is what we call the local test. The local test, if you're trying to decide, hey, I've got a vector field, I would like to know if it's a gradient, or said differently, I've got a vector field, I would like to know, is that path independent? Here's the test. The test is compute the curl, see if you get 0. And if you do get 0, then it is path independent. And if you don't get 0, then it is not path independent. Nice, simple little test right there. And so this is the way I like to do it. And of course, you got to remember gradients and path independence. Same idea, appropriately regular. So pretty neat tool. I'm going to introduce another little bit of terminology. This one I do like. Oh, you had a question? Yeah.
How does this relate to the fundamental theorem of line integrals?
We don't really particularly need it for this purpose. We've already used the fundamental theorem to connect these two ideas, right? Gradients and path independence. But it's not being used in this argument.
Okay.
Yeah. Okay, so I like the following little bit of terminology. Vector fields that have this property are called irrotational. And this is very natural language. And I like it when stuff really, is natural. So we'll start off by observing that curl, we already know, curl in some sense represents kind of how much there is a rotational aspect to the fluid. So that's where the rotational part of this terminology comes from. And pretty easy pitch, I think. If there is none of that, right, then, I suppose we could quibble and say maybe we would have preferred to call this non-rotational or unrotational, right? But for whatever reason, irrotational is the term. But it means non. So everybody see how this is really natural language? So again, I'm going to remind you that we have various ideas that are all related. We've got this idea of irrotational. We've got this idea of a gradient. We've got this idea of path independence. We're talking about the same vector fields. 3 different properties of the same vector fields. The curl is 0. It's the gradient of something else. It's got this path independence feature. 3 different properties, all the same vector fields. Again, regularity issues ignored. So let's revisit now. Some people like to call these vector fields by a 4th name, conservative. And again, I'm like, dude, we don't have a shortage of terminology here. I really don't see why, conservative is such a popular term. But do please be reminded, it is. Whether I like it or not, right? I'm not in charge here. Whether I like it or not, conservative is in very common use. And you just have to remember, conservative, again, regularity issues aside, conservative is still talking about the same vector fields. So, anyway. All right. Side note, this local test for vector fields in R2, there is an analogous local test for vector fields in R3. So again, 2-dimensional there, three-dimensional here. No surprise, it is, again, curl. That is the test. You need curl to equal to 0. Why this works? Argument's very similar to what we have here. We just don't have a three-dimensional Green's theorem yet to be able to make such an argument. But we will very soon have a three-dimensional Green's theorem, and then I'll be able to do an argument that's morally equivalent to what we did up here. That's coming pretty soon. But I do want to go ahead and get the tool in our toolbox while we're at it. Okay, so first example. Here's a vector field. Is it a gradient? By the way, common scenario. Right? In your working life as engineers, you're going to find yourself looking at vector fields, and you're going to find yourself sometimes wanting to know, hey, is this thing a gradient? Is it path independent? I need to know. And so you use the test that we just talked about, and you compute the curl. We're going to compute the curl. And we're going to try to determine, is it or is it not the 0 vector? Yeah? Okay. So you start computing the curl and something kind of lucky happens. This curl that we're computing here, you notice that we already have non-zero in the first coordinate. I haven't computed the second coordinate or the third coordinate yet, but here's the thing to keep in mind. All I care about is whether this is or is not a gradient. Therefore, all I care about is whether the answer is or is not the 0 vector. And I can already tell this is not going to end up being the 0 vector. Right? We've already got one of these coordinates has already failed. Right? And so if that happens, right, I mean, if you already get non-zero in the first coordinate, you don't even have to proceed. You already know not 0. And therefore, this is not a gradient. Is that cool? Now, this is a one-way shortcut. If we had gotten 0 for the first coordinate, and then, well, it still could go either way, and it's not clear. But non-zero, done. Okay. Everybody happy? Yeah, question.
What do you mean by it could go either way?
Yeah, well, let's consider a different scenario, and let's suppose I've got some. Let me zoom in on. Okay, so let's suppose I got some other vector field, and I'm going to compute the curl of that other vector field. And let's suppose that as I compute, let's suppose the first thing I get is 0. You see what I'm saying?
Yeah.
Now it's like, well, I could go either way at this point. It could be zeros, maybe, but it also could be not 0, and we just can't tell. So there's no shortcut for something like this. Yeah. Right. Whoa, it took me in the wrong place. Okay, here's another example. This is a two-dimensional example, so I use the two-dimensional test, which is to compute the two-dimensional curl. And again, I get not 0. So this is definitely not a gradient, right? Again, easy little tool to apply, instant conclusion. By the way, just for intuitive satisfaction, right? I always like to find satisfaction when we can. This vector field, we already know what it looks like. This is our stirred pot. So what we have concluded is that this is not a gradient, and I'm going to point out, well, yeah, it better not be, right? Because gradients always point uphill, and if you think about it, if that's uphill and that's uphill and that's uphill, if all of these directions are pointing uphill, we have an Escher-Stairs situation again. Those vectors cannot all be pointing uphill. Find me the mountain where where that happens. It's not possible. Right? Okay. All right. Okay, so easy tools to apply. All right, now I'm going to pull up. So this is y'all remember I referred to this diagram back in chapter 3. So we're here we are again. I do want to have the better version up. I should have pulled this up before class started, and I forgot. So let's see here. Give me a sec. Opening. Oh gosh, now I need my glasses. Apologies. There we go. Okay, so here's our diagram, or a sort of more complete diagram. And a few things I want to remind you of. The big idea is that we compose curl and gradient in that order. The order is critical. And that when you do so, wonderful things happen. Oh, let me point out, I made this diagram back when I was still on the GRN kick. So again, that just means curl. Okay. So we talked about that. And we've talked about the fact that, when you have a curve, it has boundary points. And when you have a two-dimensional region, it has a boundary curve. And of course, you can then take the boundary of a boundary. And this too has this kind of same feature, where if you take some region and you look at its boundary curve, and then if you ask what are the boundary points of that boundary curve of a region, you're always going to get nothing. You know what I mean? There's something to think about there. And it kind of goes both ways. So basically, there are curves like this that have a boundary but are not the boundary of anything. And then there are curves like this that are the boundary of something but don't have any boundary points. This is a little cool observations about just kind of about how geometry works, right? It's just intrinsic to space. That's the nature of space, right?
How does the pink curve have boundary points?
Yeah, this purple curve here. Well, it starts there and it ends there. That's what when we talk about the boundary of a curve, what we're talking about is the starting point and the ending point.
And because the purple one is like circular. Like
the other one, yes, starts and ends at the same point, and so you can artificially say it has a start and an end, but you're kind of making stuff up. There is no actual starting point or actual ending point. Yeah, sure. Okay, all right. So again, revisiting this diagram, and we actually now have everything that we need to talk about some really big ideas in the context of this diagram. This is going to be the first instance where I'm going to be able to hopefully drop a couple of jaws on. Wait a minute. What? How could this? What a shocking pattern. Okay, and here comes. The very first of these theorems that we talked about was Green's theorem. And here, I'll do that in green. How about that? Green's theorem, you'll recall, if you take a vector field and compute Green's operator of it, and then if you take some two-dimensional region and you look at the boundary curve of that two-dimensional region, Green's theorem says that the line integral of the original vector field over the boundary curve and the double integral of Green's operator, double integral of curl over your original two-dimensional region are the same. Right? So now, just for sort of diagram, connectivity sort of purposes, I like to streamline by saying if you do that and that and that and that, you get the same answer. So that's kind of who cares a little. But if you want to ask how does Green's theorem manifest on this diagram, then arguably that's it. Now let's do the same thing for the fundamental theorem of line integrals, and this is the jaw-dropping moment to me. If you take the gradient of a function, and if you look at a curve and its endpoints, if you evaluate in this sense the original function on those two endpoints, like so, If you do, on the other hand, a line integral of the gradient over the original curve, like so, you get the same thing. In other words, the fundamental theorem of line integrals looks exactly the same as Green's theorem on the diagram. It's the same exact pattern. Right? What? How could it? What? These are totally different theorems. One of them's about areas and rotations and circulation and stuff like that. The other one is about curves and change and gradients. None of the mathematical, well, they both involve line integrals, but they're about otherwise completely different mathematical constructions. And yet they have the exact same pattern? What? Right? Yes? Oh, yeah. Let me come back to that in a second. That's a great question, and I'll totally get to it. And just let's focus on this part first. This did not go unnoticed when they first figured out Green's theorem. It's pretty noticeable, right? And there was a big question in the math community for a very long time. Something on the order, depending on how you count, somewhere in the ballpark of most of 100 years. Right? Everyone's like, what? You gotta be kidding me. By the way, there's more. What we're going to find, this is the three-dimensional version of the diagram. We're going to soon be talking about something called Gauss's divergence theorem. And ultimately, the way it's going to show up is the same exact pattern. And we're eventually going to talk about something called Stokes' theorem. Same exact pattern, right? So all of this got observed in the early to mid 1800s, right? And a crisp, satisfying, complete answer to how could these all look exactly the same? What in the world is going on here? How do we unify all of these theorems? How do we explain what otherwise we would have to chalk up to being just a stunning coincidence? Didn't really get fully resolved until I think it was, I forget, it was somewhere in the 1930s or 1940s. Right? And again, I think I've made this comment before, but I am 2 degrees of separation from that guy. That's how recent it is. Right? So, this is pretty recent. And the math that it takes to make this, unification, right, is very impressive, right? Very sophisticated, powerful ideas. And by the way, we have already kind of hinted at what those are previously. It's differential forms. Right? So all that coordinate line integral notation that we talked about, that's kind of heading in the right direction, frankly, to make these big connections. Okay, so again, I can't tell you the big, sophisticated, super powerful ideas. It's well beyond this course. But I do think it's really, really helpful to see the patterns. Minus all the formalities and rigor and sophistication that, we can't, that's not realistic. But the patterns are completely accessible. Here they are. And they show up when you think about everything in terms of these diagrams. So my advice for your consideration, when I think about these theorems, I'm always thinking in the context of this diagram. There's really good reasons to do it, and the patterns that you'll notice. You arguably don't even have to memorize 2 different theorems. You just memorize one pattern. And the same pattern that we use here, same pattern works here. Right? So I think there's a lot to be gained from that. I haven't forgotten your question. There is another pattern that I want to establish. We've already talked about, but I want to do it on the diagram. Special vector fields. We spent some time earlier talking about how there are those vector fields that are gradients of some function. There are those vector fields for which curl is 0. And there are those vector fields that are path independent, meaning that if you look at two different curves that give you the same boundary points, then you'll always get the same line integral. So that's just this little, what I've drawn there is just how I kind of visualize, in the context of this diagram. That's how I think about these three ideas. And we've already talked about how any vector field that has any one of these three properties also has the other two, regularity issues aside. So here's a really surprising fact, and we're not going to be able to flesh this out today, but I just want y'all to be on the lookout for it. This pattern, not only does it work also in 3 dimensions, this is where it gets really weird, it also works one notch over in the diagram. And this is another jaw-dropping moment for me. Let's see, here we go. So we will eventually talk about vector fields. We've already talked about the curl operator and the divergence operator, and we will eventually make sense out of the idea of a surface integral that's coming up tomorrow. Today, Friday. Coming up Monday. But it's going to turn out that any vector field that is a curl of something will have divergence equal to 0, and vice versa. And furthermore, any vector field whose divergence is 0 will have this mysterious property that I can't really talk about completely just yet, but no surprise, we're going to call this surface independence. Right? So another situation where the diagram is paying off big time because the patterns that you use to understand path independence, the patterns that you use to understand path independence and irrotational and gradients and stuff like that, it's the same pattern over here. So again, you don't have to learn a whole new set of ideas. You just have to understand the pattern and then apply that pattern in whichever context is appropriate. So again, I'm a huge fan. I think that's really powerful. Okay, let me answer your question now. So this stuff at the bottom, so these are the lifetime theorems that we talked about. And so we talked about, back in chapter 3, I made these claims that if you have a vector field that is the gradient of some function, then the curl would have to be 0. Right? And the way I represent that in this diagram is solid lines represent the hypothesis, the assumption that you work with, and then the dotted line represents the conclusion that you can draw from that assumption. So this says if you have a gradient, then curl is 0. And this says if curl is 0, aka if it's irrotational, then you can conclude that that is the gradient of some antigradient. That's all that means there. Is that cool? Yeah. All right. I think these diagrams are really super. I hope you'll enjoy them. Oh, yeah, and there's some really good computational hints that come out of it as well. So if you're looking at a line integral, and you're trying to decide, well, hey, wait a minute, can I use the fundamental theorem of line integrals to compute this line integral? Right? Reasonable question. Again, you've got a toolbox full of tools. And you don't want to try to apply the wrong tool if you don't have to. I mean, you can go straight to what is the correct tool, what is the best tool to work with. Wouldn't that be nice? Well, how would I decide here if I could use the fundamental theorem of line integrals? Well, I need to know if there's an antigradient. That's the big test. Now, whatever the curve is, I know I can look at the boundary points. There's no challenge in finding boundary points. You just look at the curve and see where it starts and ends. And if it's a closed curve, then pick whatever points you like, right? That part's not a problem. The problem is knowing, is it a gradient? And the diagram tells us how to determine the answer to that question. Now again, you can memorize theorems, but I think it's easier to just look at the diagram and be like, all right, well, if I want to know if there is or is not an anti-gradient, take curl, see if you do or do not get 0. Does that make sense? And notice further, if in fact you have a line integral, well, that line integral will come with a curve. Of course, you got to know what the curve is, and it'll come with an integrand. Of course, you got to know what the integrand is. Now, the diagram, I don't even really have to know that I'm entertaining the question of whether I can use the fundamental theorem. The diagram says, hey, you know that vector field you've got? Right here, it tells me, hey, that vector field, you should compute curl of that. It just straight up tells you what to do. Right? And that's another pattern that's going to continue when we later on get to the point where we're talking about these surface integrals, for example. Well, there will be a vector field, and the diagram is straight up telling you, hey, what should I do with that vector field? Well, I should compute the divergence of it. It's telling you what to do. And I think that's pretty great as well. So I'm going to be coming back to this diagram a lot. I think it's tremendously valuable for, again, noticing patterns, benefiting from seeing how, look, all these ideas we're talking about are just the same ideas in different contexts, right? And it's helpful for problem solving. It's helpful for intuition, because once you develop an understanding in one context, you can apply that to a different context. It's just tremendously valuable. I'll be coming back to this a lot, and I urge y'all, download this file. It's in the class materials folder, I believe, from the class website. If I got that wrong, let me know. But it's definitely, it's either the class materials or course materials. I'm pretty sure it's class materials. And then as we're going through, I urge y'all, have this handy. We're in 2 dimensions for the moment, so 2-dimensional diagram. Have this handy, and everything that you see, every idea that you look at concerning all this kind of stuff, find where that is on this diagram and think about it in that context, and it will be very helpful. Okay, moving along. How do you find anti-gradients? This is actually a pretty easy observation. Y'all may have kind of already effectively figured this out for yourselves. But notice, if you want to know if a vector field is a gradient, what you're really asking is if these coordinates can all be partial derivatives of the same function. And, well, wait a second. If P, Q, and R are the X, Y, and Z partials of F, then, if P, Q, and R are the X, Y, and Z partials, then that means that F has to be the X, Y, and Z anti-partials of P, Q, and R. Now that's just a sort of a grammatical rephrase. It's not really anything new, right? Of course, now if you're talking about X anti-partials, the whole point of adding in a plus C is that I'm looking for something that when I take the X partial, you'll get 0. And typically that means that this has to be a constant, single variable calculus. Something whose derivative is 0 is a constant. Right? But now we're talking about things whose X partials are 0. Those don't have to be constants. They just can't be functions of X. Right? So this could be any function of Y and Z. What we call a partial constant. Awkward language. Kind of oxymoron language, right? Partial constant. Kind of constant, but not really. Anyway, but that's a term. It's just a term. Any function of Y and Z, and likewise, this can be any function of X and Z, and this can be any function of X and Y. And so what we have here is a kind of a game. What you're going to do with a given vector field is you're going to look at the x antipartial, y antipartial, z antipartial. Don't forget your partial constants. And you're going to look at these three things. Example on the next page. You're going to look at these three things and ask, is there a function that could equal to all three of these things? Because that's what f has to be. If you're going to have an anti-gradient, if your vector field is going to be a gradient, it therefore has an anti-gradient. That anti-gradient has got to equal to all three of these things. And you just play the game and see if you can. So here's the example. P, let me do it like this. P Q R, as described previously, we take the x, y, and z antipartials, which give me these. Don't forget your partial constants. Right, all I've done here is just write down what we, set up on the previous page. Thus begins the game. I need for this and this and this all to be equal to each other. Now, it kind of looks like it's an obvious fail because they're different expressions. But you know what? Those C1, C2, and C3 could be anything. Right? So here's what I propose. I see this x squared y and this x squared y, and I see that there is none here, but or maybe it's hiding inside of there. Right? So I can make x squared y a b in all three of these expressions if I just choose C3 to be x squared y. And then likewise, that and that could be what that is. And likewise, that and that could be what that is. And we win, right? These three things can all be equal. And they're all equal to this expression right here. So this is our anti-gradient. The vector field we started with is a gradient, and we have found the anti-gradient. Does everybody see how that goes? It's a quick little game, right? You take the appropriate partials, don't forget your partial constants, play the game, win the game. On the other hand, we know sometimes we are doomed to lose, right? Earlier we talked about this vector field. We showed that curl is not zero. So there is no anti-gradient. Oh, this is a typo. Sorry, I'll fix this, but that should be little f. There is going to be no anti-gradient here. So now wait a second. If we've got a procedure in the form of a game that finds anti-gradients, what happens when there is no anti-gradient? And the answer is you lose the game. Right? It's as simple as that. So let's see how it looks when you lose the game. Well, this is what the game ends up being. I need to think about how I can choose C1, a function of only y, and C2, a function of only x. That makes these equal. And good luck. You lose. Right? Not going to happen. And thankfully, it better not happen. We already knew that there is no anti-gradient. Right? If you could win this game, Escher stairs would be possible. Not good. Okay, that's a pretty good place to draw the line. So we will pick up here next time. Y'all have a good one. See you later. Whoops.